Okay, thank you for joining us as we continue our discussion with vectors. And for our work today, we're going to be looking at the intersections of planes as well as the intersections of planes with lines. All right, so we'll be going over systems of equations in this lesson, equations of lines, their relative positions, equations of planes, scalar products, vector products, and intersecting planes and lines. But this video will focus initially on the intersection between two planes. And we'll look at two different ways that we can work with that. So let us look to our first couple of problems. So we have a plane, 2x plus y minus z is equal to 3. And we have another plane, x plus y plus 2z is equal to 5. And we want to determine the line of intersection between the two planes. And we know that if we have two planes, we are going to end up with a line of intersection. And the main reason for that is because of how our planes must align with one another, that we will have some line of intersection between those planes. Okay, if we have two planes, we know we're going to have a line of intersection. So our first example, we're going to talk about how to solve algebraically as well as how to use a calculator, and you're going to want to be familiar with both approaches. So our matrix approach, which is essentially nothing more than an elimination approach, is to start with creating our matrix of coefficients. And so we're going to have 2, 1, negative 1, 3 for our first plane, 1, 1, 2, and 5 for the second plane. If I keep, if I keep row 1 the same, if I keep row 1, but then subtract row 2 from row 1, so I say row 1 minus row 2, that's going to keep row 1 the same, 2, 1, negative 1, 3. And the subtraction will lead me to 1, 0. Negative 1 minus 2 is negative 3. 3 minus 5 is negative 2. And if I do my row reduction once again, because I'm going to try and create 0 in two different locations, what I'm going to do for row 1 is I'm going to say row 1 minus double row 2 now, and I'm going to keep row 2 the same. The reason being is I want to keep this 0 here, but I want to try to make one of the other spots 0, and I'll just go ahead and make this position 0 there. So if I take row 1 and I subtract double row 2, so 2 minus double 1, right, that's going to give me a 0, right? Excuse me. I'm going to keep row 2 where it is, 1, 0, negative 3, negative 2, right? Then I'm going to take this minus double that, that's 0. Take this minus double that, that's 0. Take this minus double that, so that's negative 1 minus negative 6, which would give me a 5. And then this minus double that, that would be 3 minus negative 4. So that's going to give me a 7. And so what this tells me now is I have a relationship between my x, y, and z values. Right? That I have x is going to be equal to negative 2 plus 3z, looking at this second row where I have essentially my x, my y, my z, and my constant. And then from the first row, I have that y is going to be equal to 7 minus 5z. All right, so then I know that z is going to be equal to z. So if I want the equation of the line of intersection, that would be a parametrized form of the equation. My vector equation would be r equals, all right, coordinate points, negative 2, 7, 0, plus some parameter, and then the directionality of 3, negative 5, and 1. So that would be my equation, and this would be done using a algebraic approach. If I wanted to do this with a calculator, I can solve it rather simply, going into my equation solver, and I can come to my equation solver and go ahead and add an expression, and we know that we're going to have a system of equations with two planes. And so let's go ahead, and our first equation is 2x plus y minus z. So 2x plus y minus z is equal to 3. And my second equation is x plus y plus 2z is equal to 5. All right, and if I solve this equation, you'll notice that I have x is equal to, right? So solving this equation with a calculator is that x is equal to 3t minus 2, y is equal to negative 5t plus 7, and that z is equal to t. So that would be the parametrized form of my equation. We know that we have an infinite number of solutions, and of course we talked how we could get it to the vector form. If I wanted to do the Cartesian form, I could write this in Cartesian form as well, but we won't worry about that at this time. Okay, so pause for a moment, think about what's been presented, and we will continue with the next example of a different way of finding the intersection between two planes. And that intersection will always be a line. Okay, so continuing. Like we said, that intersection will be a line if the planes aren't parallel or coincident. So let's look at our next question. Okay, number 2. And for this question, once again, we have two planes. And here we're going to be able to verify that we have a point that lies on both planes. And then we're going to want the equation of the line of intersection between the two planes. And the idea here is that the normal to the normals is the direction of the line of intersection. That if I have one plane, right, and it intersects with another plane, and I have a normal for one plane and another normal for the other plane, then that normal that is perpendicular to both of those normals will be the direction of the line of intersection. All right, so let's start here. We start with verify that we have a point on both planes. So how can we verify we have a point on both planes? All right, is that point 6, 1, 2? Does it work for both equations? All right, so if we look at it for plane 1, we have 6 plus, so 6 plus 1 minus 2 times 2, and that's going to equal 3. And if we look at plane 2, that's going to give us 2 times 6 minus 3 times 1 minus 2, and that gives us 12 minus 5, and that's equal to 7. So therefore, we know that 6, 1, 2 is on both planes. So that point must be along the line of intersection. So how can we find the equation of the two planes? Well, we know the general form of the equation is going to be given by, my vector equation will say, is going to be a point that's on both planes, so 6, 1, 2, and then plus, right, some directionality vector. How are we going to find this directionality vector? It's just going to be the normal to the normals. So I'm going to come over and take 1, 1, negative 2. So I'm going to want to have 1, 1, negative 2. And I'm going to want to cross that with 2, negative 3, negative 1. There's a variety of ways that I can work on this cross product. Some people use the determinant approach, which is perfectly acceptable. And so if I'm going the determinant approach, I have a vector 1, 1, negative 2, and a vector 2, negative 3, negative 1. If I look towards this cross product, right, in the I direction, I'm going to have 1 times negative 1 is negative 1. I'm going to have minus negative 2 times negative 3, so that's minus 6. Then I'm going to have in the negative j direction, 1 times negative 1, which is negative 1. 2 times negative 2, which is negative 4. Subtract that, becomes plus 4. And then in the k direction, I will have 1 times negative 3, which is negative 3. 1 times 2, which is negative 2, so then subtract. And that's going to give me negative 7 in the I direction, negative 3 in negative 3 in the j direction or the y direction, and negative 5 in the k direction. So what does that mean for me? What that means is that I have the directionality of my line of intersection, right? And if I factor out the negative, that just gives me the line of intersection having equation 612 plus mu times 7, 3, 5. So a couple of approaches for finding the equation of a line of intersection. If we know a point on both planes, then certainly this cross product approach is a bit more efficient. If we have a calculator, we need to understand what the calculator represents. And of course, we can solve by elimination or by row reduction to get to our solution. So we have the vector equation of a line. We have the parametrized equation of a line. Vector equation, once again, that being the most common. But of course, we could also talk to the Cartesian equation of a line. In this case, we would have x minus the x point all over the directionality, y minus the y point all over the directionality, and equal to z minus the z point all over the directionality. So this is one form of the equation. This is another form of the equation. Which one we should use is completely up to what the question asks or your preference. All right, let's go ahead and solve this last one with a um, calculator anyway. All right, let's see what we have. So we had, let's see here, x plus y minus 2z being equal to 3. And we had 2x minus 3y minus z being equal to 7. And if we look to solve that equation, right, we can see our solution and we say, well, hey, I don't see how this matches. Well, let's look at what the coefficients of t are. I have 7, 3, and 2. But look, this is divided by 5, so let's multiply everything by 5. I would have 7, 3, and 5, and there's my directionality. So with that, we actually also know another point that is on the curve, but which approach you use is completely up to you. Thank you.